Hello, everyone. So today I'm going to talk about a kind of simple problem, but taken to a very large extreme, so that so that it kind of has to be solved using simulations instead of being solved analytically. So the problem that we're solving is, to put it simply, given a deck of cards, what is the expected number of draws that you need to do before getting two cards of the exact same number? So if we imagine having cards 2 through 10, and then each card has four suits, what would be the amount of the expected amount of draws that you need to do before getting two cards with the same number but different suits? And that's the answer or that's the question that we're trying to answer. But the main obstacle is that instead of 2 through 10 and then 4, our card numbers are actually banknote serial numbers. So our serial numbers go from 1 to 96 million. And instead of 4 copies per card, we have 12 regional banks that each have, their own amount of copies that have the same serial number, and then plus the amount of copies for each bank. And we can actually look at that data set right now. So the data set that I'm using for this problem is the 1988A data set for $1 bills. So this looks at the total amount of bills printed from April 1990 all the way to about August of 94. And it shows you, how many bills have been printed and how many copies of each serial number has also been printed. Because each of these will start at 00001, and they'll go all the way up to 96 million, and then this letter will increment, and then they'll start again at 1 and then go all the way up. So each of these regional banks not only starts with the same serial number and goes up, but each of them has a different amount of copies of that serial number. And at the very end, we actually can see that the banks do not make a perfectly even amount. They don't make exactly 96 million of every serial number. I mean, some of them do, but some of them don't. So we actually solve this problem twice. The first of which, not including these partial batches, not including serial numbers that don't go all the way from, or copies that don't go all the way from 1 to 96 million. And then the second problem, which is much harder to solve, is if you actually include this, then how does that change the probabilities? And I can discuss the first part of the problem, the excluding partial batches, pretty simply, because really it does not involve a ton of math. So the whole simulation can kind of come down to this picture, where D is the number of cards drawn, R is the number of copies per card, and N is the number, or I guess not per card, but per serial number. And then N is the number of unique serial numbers. So essentially what this does is, so the number of cards drawn multiplied by the number of copies per card minus 1 is the amount of cards in the deck that match the serial number with the card that you own. Because the number of cards drawn times R is the total number of cards with that serial number, or with the serial numbers that you own, but it's r minus 1 because since you've already drawn one, it's outside of the deck and you can't draw it again. And then n times r minus d is just the total number of cards, or the total number of bill serial numbers, times the number of copies per bill, minus the amount of cards already drawn. So that's equivalent to the total amount of bills that are not in your collection, that are still in circulation. And so this is essentially the probability of getting a card that matches over just getting any card whatsoever. And if that probability ends up being true, if the probability quote unquote hits, then we have a match, and then all we do is just return the total amount of cards drawn. And if the probability doesn't hit, if we don't draw a match with our one draw, then all we do is we increment D, which means we drew one more unique card, and then we reinitialize this draw card event. So that's really the whole thing for the non-partial batches. But the issue with partial batches is instead of being able to uniformly, draw any card without really worrying about it, the probabilities are now non-uniformly distributed. So, we'll have some amount of cards that have like 20 copies, and then we'll have some amount of cards that only have 5 copies. And it's going to be, much, much easier or much more likely to draw from this size of 20 copies than to draw from cards that only have 5 copies. So instead of being able to just use a singular probability, we have to do a lot more. Also, because, these batches have different copies, instead of being able to put all matching cards and all non-matching cards in individual buckets, now the non-matching cards have their own buckets inside. And instead of just grabbing a number from this whole bucket, we have to figure out which of these buckets we grab a number in, which just involves an extra layer of algorithms. But I do end up running the simulation, and another part that I missed is that if we imagine that we already own K cards, then what is the expected number of draws? But I did run the simulation for various numbers of K, from 0, 10,000, 30,000, 100,000, and 500,000. And we have to remember that these numbers are very big because we're drawing from, 96 million individual numbers. So we have to imagine that we have a pretty substantial collection already in order for it to make a real difference. But we can see that, and I have both the histogram for excluding partial batches, which is this one, and then the histogram including partial batches, which is this. And we can see pretty clearly that the expected value is roughly normal, or the distribution of the value is roughly normal, but as we already own, or if we already own more and more cards, the distribution becomes more and more skewed. And we can see here that basically exponentially, with more and more cards already owned, the expected number of bills drawn before a match decreases. And I believe that is everything. So I hope you enjoyed. I will see you later. Bye-bye.